it's probably pointless to try to apologize. And it's very embarrassing. I taught you something in this course which was finished exactly 100 years ago. I basically taught you nothing that wasn't formulated 100 years ago. And I think it's criminal. And as you didn't express any wish to be taught something else, today I'll teach you forbidden stuff. You will not see H bar. You won't even see I, the complex unit. Because the way we teach physics, my extremely conservative colleagues who are afraid to do anything that somebody else has not done before, very authority struck, you get lots of trees, but you never see in the forest. The way this is taught is just not at all a modern thing. So my goal today is to teach you quantum physics, systems with noise, field theories, thermodynamics, chaos, any situation in which you have very many little pieces that you have to put together, hydrodynamics, turbulence, whatever. And how do you do that? And we know this in stages. We know it from thermodynamics before we knew anything else. From 19th century, we know it from electromagnetism, and we definitely know it from quantum field theory. I will teach you now like you've never seen anything. You've entered a physics classroom for the first time. The version I'll teach right now, the first version, is due to Schwinger, generating functionals. We say there are things that we call particles. And what particle is a list of attributes, which I'll compress all in one vector index in a very, very long array, which takes care of what kind of particle, what color is it, what spin does it have, which way it points in space-time, where am I looking, etc. So when I define a theory, define all these things, so what kind, type, color, spin, direction, coordinate. We call this functional because some of these things are discrete, some of them are vectors with finite range, some of them are discrete with infinite range, some of them are continuous. Now, once we have a particle, it has to do something. So what can a particle do? It can change into same particle with different attributes. So I start with particle J, I end with particle I. I'll find it much easier to draw pictures than write formulas, but it's up to your taste, what you understand better. So doing something means, for example, you change your position. And the contact with quantum mechanics we have learned so far, and statistical mechanics you might have learned elsewhere, that I assign to this change something, a number, real complex number, which could be probability, amplitude. That's one thing you could do. But you can also say, I'm not alone in the world, there are other particles. I want to interact with them. Three particles can come together, specified by their complete set of labels, and they can do something together. And I assign, again, a likelihood, some number. So again, this is a number, real or complex, that explain this. There could be 4 of them getting together. So the picture will be 4 legs. So these are interactions. Finally, I can be a deity, and I can either create or destroy. I can be a Vishnu. So I can take a particle, and just nix it. So depending, how I think about it, for example, if I had temporal ordering, I might think about things that pop up, they are created. I have a source that creates stuff, or I can destroy. That's called sink. So that's the most general possible setup. What did Schwinger make out of this? He said, well, let me define something that, in very general sense, is a Green's function. So think of it as a cloud. What happens is some number of particles come in, and for every disposition of this particle, I have every fixed set of labels for them. I have a value that I'm supposed to compute. Remember, I was given these so-called Baire interactions. 3 of us can do something, but now the Green's function, correlation, expectation, it has many names, is the sum of everything that happens, restricted to things which are allowed by law. For example, I cannot have one electron come in and no spinning particle come out or something. So there are all kinds of rules that says certain combinations are zeros and other ones are not. Here you write everything that can possibly happen. As an example, if 3 particles enter into a bar, a Catholic priest, a mullah, and a rabbit, a misspelled rabbi, they enter the bar. It's very foggy. And, now you have to count all things that could have happened. So they could have just interacted in the simplest possible way. And again, pretty soon you realize you don't have to put these letters here. You can, you can label them anytime. Once you draw pictures, it doesn't really matter. Then, other things can happen. For example, I can split into, talk to 2 particles, which then go dancing with some other particles, while all kinds of things are going on in a bar which are disconnected from me. I'm not interacting with them. So this is a huge sum. And there's some topological thing you can say about it. There's things called tadpole, and something else is happening. Which is only interaction between these 2 other people that now I've lost touch with, etc. So that's a Green's function. This one has 3 legs. It can have 4 legs, 5 legs, infinitely many legs. For every Green's function, I can now describe the rule by which I enumerate all possible things that can happen. And I can be very systematic about it. This way of thinking is all from not 100 years ago, but from 1947. Dyson-Schwinger. What they say is, this has lots of legs, but let me see what happens if I take one leg and I pull it out. So now you think of this as you're a fisherman, you have a net in the ocean. You take one rope in this thing and you pull it out and see what happens next. So it's very intuitive, obvious thing. Now, as I pull this leg out, the simplest thing can happen is that I pull on a piece of rope, but it's actually not attached to my net. I go from particle I to particle M, whereas all this other stuff peacefully does whatever a fishing net would be doing. So that's one thing that can happen. Other thing that can happen is I pull it and I realize that I had this rule, you can have many rules where 7 people interact, but simplest one is where, 3 interact. So I pull it out and I find a knot and it continues as 2 pieces of rope. Pulled out my eye here. And what remains, notice this Green's function had 5 legs. It's related to one with 3 legs if it's disconnected. If it's connected, it's related to one with 1 leg more in this particular case, because all the other legs are still around. When you think about it a little bit, you realize it's convenient. Whenever this happens, you can distinguish who is first, who is second. It's convenient to divide it by 1/2. That's just combinatorics, not important, but convenient. So that's Dyson-Schwinger equation. But we're talking about generating functionals. There's nothing special about having 3 people, 4, 5, 6 people interacting. Let's define z of j. In statistical mechanics, this is called partition function, but if that helps. It says, this is a sum from m equals 0, nobody's there, to infinitely many people interacting, 1 over m factorial for these combinatorial symmetry reasons, times a Green's function. So Green's function is this thing I just wrote here. If I insist to write it like Schwinger did without drawing pictures, I write an expression. An expression for this 5-index array where for any particular value of the labels ij, k, l, m, g, or Green's function of ij, k, l, m is some number, real or complex. So I have a big array indexed by 5 indices of these things. Now, there's nothing special about having 5 legs, 3 legs, 7 legs, 27 legs. So it's very convenient to combine all these Green's functions with different numbers of legs into a generating function. And the trick about a generating function is that in it I combine the processes with no external legs, with 1, with 2, 3, 4, 5, all of them. And the way I combine them is that I write the Green's function with a certain number of legs. I contract each of the leg with my sources. ji1, j2, 1, j3, 1, etc. And then it's natural, because of the symmetry of this multidimensional array, to divide it by 1 over m factorial. And that's my definition, or Schwinger's definitions of generating function for all Green's functions. Now, you might think that because I'm summing over everything, I've lost some information, but that's not so. If I now start taking derivatives of the generating function, and after having taken the derivative, set all sources equal to 0, what I get back precisely is that original Green's function. If I have, m derivatives, I'll get the Green's function with m legs. And that combinatorial factor is helpful because in the process of doing this, it'll cancel out. and I've lost no information. Having a generating function or having individual Green's functions with finite number of lengths, it's fully equivalent, but generating functions are wonderful because I can manipulate functions themselves in a very powerful and convenient ways. In particular, this fisherman's strategy of pulling one piece of rope out of the ocean to probe Green's functions, I can write that as a first derivative of partition function with respect to J with a given label I, particular state. And what's beautiful about this is that at one fell swoop, I can get an equation that applies to all Green's functions, no matter how many legs they have. So remember, I either just pulled a source term out, just a piece of rope, that gives me this two-point Green's functions or a propagator connecting me, who is pulling at I, with just falling out a J. Or I pulled out a knot which had continuations in two pieces of rope going into the net. That means two derivatives here. And of course, there are always these combinatorial factors. And now, depending how many of these interactions denoted by little gamma I have more of such terms, and all of them simply act on the partition function or generating function. And that's now a Dyson-Schwinger equation, not drawn as pictures of pulling out a net from the sea, but as derivatives of a generating function. So now it's a little bit tedious to keep writing all these things with all their gammas and indices, etc. So let's compactify the notation a little bit by collecting what we call bare vertices of theory in another function. Now, that function can be very short, depending where I have finite number of vertices or interactions, as I tend to have in quantum field theory. Or I might have infinite numbers of these interactions. That happens in general relativity. But I now write a function called action, function of some variable phi. I combine what I have. It turns out it's convenient, this two-point Green's function. It's like a matrix, so I can invert it. And it's convenient to introduce it in the action as its inverse, as shows up in computations, and then combine everybody else in this list in something that we call interaction part. So these are all these gammas that combine three or more fields together. Again, this interaction part is typically a short finite polynomial, or multinomial. So now that we have defined this function, what we can do is we can replace phi by the derivative with respect to j and get a compact form of Dyson-Schwinger equation. We will have a distinction between what we call bare theory, meaning just the particle not accompanied by other stuff. That's called dress theory. So this action collects all the bare terms, all possible interaction. And what it actually is, it's extremely efficient and compact way of listing all symmetries of the theories, because we allow only interactions which are compatible with the symmetries. So now is the Dyson-Schwinger equation written in a Schwinger way. I put the left-hand side over on the right. I multiply everybody by this inverse of delta ij, the matrix which is the propagator. And what's in curly brackets, I just write it as this function. But with the field, this variable phi has no significance, it's just a variable to help us manipulate functionals. Replacing this phi by the derivative with respect to j. And now Dyson-Schwinger equation takes a really nice compact form. It's this action, first derivative of it, meaning I was pulling one leg out. And it says the action plus the source acting as an operator, meaning derivative with respect to j on the partition function has to be 0. And that's the Dyson-Schwinger equation. It relates partition function z to the laws that we impose on the system, which are all listed in this action S. Now, I've already shown you how you use this. You use it recursively. You pull out the leg. The Dyson-Schwinger relation, what it does is it relates pulling out the leg to either going out to the source, or, this is the j term, or to Green's functions with more external legs. And as you keep repeating this, you actually produce all possible interactions, basically ordered by the number of the bare interaction vertices. So if these bare interaction vertices are small numbers, for example, in quantum electrodynamics, they are weighted by fine structure constants. So each vertex is, vaguely speaking, 1 over 137. One can order the diagrams that are being generated this way. These are the all possible diagrams that contribute to all possible Green's functions, but you can order them from few vertices to more vertices and eventually truncate it.